We're going on to topic 2 of chapter 8 in Math 1127, which deals with union. Remember, the key word for union is or. Intersection, the key word is and then complement of events and odds. And this is on page 385 in your textbook. Now, a little review. The probability function in general is the probability of a specific event is a ratio to the sample field. So the most common use perhaps is a die, one dice. There are 6 sides, so any one event would be 1 out of 6. But in example 1 on page 386, they're giving us a particular set of numbers. 1, 2, 3, 4, 5, 6. If I put that in sort of a Venn diagram, there they are. Now, what they're asking is, what's the probability that an example would be of this set would be odd and exactly divisible by 3. Well, these are the numbers in your set that are odd. 1, 5, and 3. But then the numbers 1, 5, and 3, now I've put in this little Venn diagram. The 3 is odd. The 6 is divisible by 3, but it's not odd. So how many items do you have in the event that you're looking for? Well, it's odd and exactly divisible by 3. So it would be the intersection over here of your subsets A and B. And the only member in that intersection point is 3. So this would be then your 1, 3 over the 6 possibilities in your original field, and your probability then, I guess I don't need that one, is 1/6. And by the way, we are rolling a die here, a single cube with 6 sides, an honest die. And now we're looking for the set that is odd or divisible by 3. So here we're looking for or, which is a union. So up here we're looking for a union of this. So these are the odds, and then this are the ones that are divisible by 3. So how many items in your event if we make a union of that? Well, your probability will be 4. And then our basic group was 6 on a die, so that will be 2/3. I should have stressed that before. The other time it was and. That would have been intersection, where we're only interested in the 3. But when we go to or, we're looking union of that. That would be A union with B. I wanted to go over this a little bit before too, but it's never too late. Here we have a series of Venn diagrams. And in this Venn diagram, we're asked to show union? Well, we show union by shading everything. That would indicate union. And the key word here, again, is or. In an intersection, which is an and, the only part we shade or show intersection is where the two overlap. And we would say that set A and set B are not mutually exclusive. And then we have this, in which set A does not have any contact with set B. So we say in terms of a union, there is no union, it's an empty set. And set A and set B are mutually exclusive. Another word we could add when they are mutually exclusive, as a review, they are disjointed. That is, they're not connected. And this leads us to the formula over here, that if we have the probability of unions of two events, that would be, in this case, the probability of A plus B minus the point of intersection. That is, if they're not mutually exclusive. If they are mutually exclusive, then it's just this formula. So we sort of have made two of them. This is if they are mutually exclusive, it's just the union of A and B. But if there is intersection, remember we dealt with this earlier, you have to subtract the intersection. So again, there are many formulas. We'll be working some of them, and you know, you're going to do your practice and your quiz bees. As we move on to example 2, we're dealing with dice. Remember, that's two sets, and we say they are fair. That is, they're not weighted, but the results hopefully are random. And we're still dealing with probability, the event you're looking for over the sample field. And they're asking, what is the probability of the sum of 11 or a 7 shows up when you roll these two fair dice? And a hint I gave you, because you probably won't remember this, is to make a little chart like this, where you start with 2, go to 12, and the one that's the greatest possible combination is your 6. So then this was 1, 2, 3, 4, 5, 6. As you roll the dice, 7's going to come up 6 times. A 6, 5 times. A 5, 4 times. And then from the 6, you start going down. And if you do this a couple of times, that'll be something that's very useful on your test. Of course, you can make a little chart like that for your practice and quiz bees. So we say, since it's an or, we want the sum of the number of times, and 11 will come out. So we look at our chart, 11, there's going to be 2 times. Now remember, there's 36 possibilities. And the number of times the 7 will come out is 6 times. So the event that you're looking for is a union between these two because of the or, and that gives you 8 out of 36. which is going to be 2 out of 9. The other day when I was doing some quiz-mes on this section, I left it like this, and they counted it wrong. Oh, that hurt me a little bit. You have to reduce it. So 4 times 9 is 36, and 2 times 4 is 8, so it reduces to that. This next one was a little tedious, so I wrote a lot of it out. But he says, what's the probability of rolling 2 fair dice and that the results are the same? Well, what would be the same? Well, 2 1s, 2 2s. And then how many events are there here? Well, this is 6 events. And they are, or I should say, the key word here is or, because you're having a union, but are less than 5. So our less than 5, here our groups are this, 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 and this. Now, in this particular union, we have some duplication. Notice this is duplicated, and this one and this one are duplicated. So when you count these up, you're going to use the union of them minus the intersection of these, which are here and there. So this is 12 minus 2 is 10 over 36, and that reduces to 5 over 18. So that would be your probability. Again, if you leave it in this form without reducing it, they're going to count it wrong. Now, if you're taking a test here and you get that, I think we would give you credit for that. Have you tried making up one of these results of rolling a set of dice? Again, that'll be a good tool. Well, let's go on to example 3 now. It says, what is the probability of a number selected at random of the first 500 positive integers? Now, these would be counting numbers, and which is exactly divisible by 3 or 4. And again, you might say, do you have to write all those numbers out? And the answer is no. The technique for finding those divisible by 3 is to take 500 divided by 3, and you get 166 and a little decimal. Disregard that decimal. There's 166 numbers that are divisible by 3. Do the same thing for 4, and that gives you 125. Now, in this next case, you're going to find that some of these are the same number, because if you multiply 3 by 4, you get 12. Now, 12 is the lowest common denominator between these two. In fact, when I was doing one of the quiz-mes, I was getting the wrong answer because they had a number like 24 here, and I had to take the lowest common denominator of something. Anyway, so you have to be careful about this. So these are numbers that are going to be the intersect of these. That is, they're going to be found in this set and in this set. So in order to get a fair set, you have to subtract this number from the sum of these. And actually they're in a fraction form, because this is going to be 166 out of 500, 125 out of 500. These will be multiples of 3, multiples of 4, and these will be multiples of 12. Well, and that'll be 500. Now when I add these up through my knowledge of this, this adds up to 250 over 500. Very fortunate here to have a nice round number like that. And in fact, if that's on your test or quiz me, and if you can remember this, this is a good one, then this is going to reduce to 0.5 or 1/2. Again, the technique is dividing 500 by 3, dividing it by 4, and then in this case, those that are an intersection would be the combination of these two. Those have to be subtracted. Again, I feel it's a good use of time to do review. So one of the things we mentioned earlier was the complement of an event. So here is our sample field. And then within that we have set E. Well, everything not in set E is said to be the complement of E. So if we take E in union with the complement of E, we get our sample field. If we have the intersection of E and E complement, these are disjointed. There is no member to that set. So it's an empty set. So if we look at it this way, E plus the complement of E, that equals 1 or the whole of something. Now, if we use a little algebra, what does E by itself equal? Well, we just take our positive E complement to the other side, and it becomes the negative E complement. So the E value is 1 minus the complement. And the complement would be equal to 1 minus set E. So look these over. These are all from the textbook. I simplified it just a little bit to make it a little easier. And then we'll work some problems. All right, we're going to continue. We have one of our graduate tutors who will introduce himself to this next little example, example 4.
Hi, how are you? My name is Mahdi. Today I'm going to explain this question for you guys. The question says we have quality control 45 precision parts. We have 9 defective, and we have to select 10 at random. And we will reject the shipment if we have more than 1 defective item. So, to start solving the question, we say like this: we have 45 items, and from those 45 items we have 9 defective, and non-defective ones are 45 minus 9, we will be ended with 36 non-defective items. The idea here is to find PE complement by using PE. So instead of finding the probability of getting defective items, we're going to use the probability of non-defective items. So here, probability of E complement is, we're going to choose C 36 out of 45 which is here, over C, or combination 10 choose 45, which is, we have to use here 10 items. We're gonna choose them from the non-defective ones. And this is the probability of getting non-defective items. By doing so, we're gonna get 0.08, which is the probability of non-defective items. But the question is asking us to find the defective items. So to find the defective items, we have to subtract 8% from 1, which is the 100%. So 100% minus 8%, we will be ended with 92%. So by using the complement, or PE complement, we can find the probability of getting a defective items using non-defective items. Thank you.
Going on to example 5, this deals with a birthday problem. It says, let's say from a group of 40 people, what is the probability that 2 or more have the same birthday out of a year that contains 365 days? Well, again, this is another example where the complement of what you are looking for is a little easier to figure out. And they do have lots of calculations in your textbook on page 390 that goes over this. But basically, to find the complement of E here would be 365 prime times 365, and then N is the number of individuals, and the one they're using in the book is 6. Instead of 2 or more, they're saying, well, let's say 6 have the same birthday. And then it's this as well, but I forgot the factorial there. Now, when you calculate this, if we are using N as 6, then it's going to be 365 to the 6th power. And then you have to subtract 6 from 365. That'll give you 359. Now, if you put this into your average calculator, raising something to such a large factorial is beyond the ability of the calculator. So the way the book suggests that you do it, and this is a technique from an earlier section, we write 365, 64, 63, 62, 61, 59, 60 I should say, end up with 359 factorial, because down at the bottom, 359 factorial, these then cancel out. So you can do this in your calculator, divide it by this, and that'll give you around 0.96. And remember, we want to find what the probability of our big group is. So we subtract it from 1. This is our complement value, and our answer then is 0.04 would be our probability. Again, all the work is in the chapter textbook pages, and they also give a little chart here that an interesting thing happens. It says you would only need a group of 23 people to have at least 50% probability that 2 people are going to have the same birthday. So most of our college classes and most of our classes have about 25 people. So there's a 50% chance, a little bit better than that 2 of those people are going to have the same birthday. Now, as we go on to our next little part of topic 2 in chapter 8, we're talking about probability and odds. Now, again, if you're a gambling person, you might know a lot about this, but if you're not, it may seem a little strange for you. And these are some of the formulas that were written up in the book, but I want to give you a little bit of background as we talk of a fair games. What is fair games? It's when all items are random and equal, that the results are not fixed, so that you get a weighted die, so one side comes up more often. Now, one of the examples they give for a fair game is, suppose you have a single die and you want to roll, let's say, a 2. What would be the probability that you would roll a 2 out of 6 possibilities? Well, that would be considered as 1/6. And then out of how many would that be? Well, now you notice that you've taken 1 out of that, so what is left is 5/6. So in figuring out odds, what we do is this actual calculation. We're going to go 1/6. Remember, we're changing this from a division to a multiplication, and that becomes 6/5. And then the 6 cancel out, and our odds then become 1/5, and it's usually read as 1/5. So that are our odds. Another way of looking at odds is you want the 2, so there's 1 of those, and then what are things you don't want, in a sense, and there's 5 remaining. So this gives you the 1/5 odds. Now, in a fair game, what you want is, if you bet $1 to get the 2, and I know this is tied into gambling, but trying to make it into something where it might have sense to you, then by placing a $1 bet that you're going to roll a 2, to have this a fair game, the house has to give you a $5 win. Now, notice, if that's how the house set things up to have a fair game, theoretically, at the end of the day, they're not making any money at all. So they may only give you $4 for that. That way, toward the end of the game, with all the averaging of the gambling that's going on, they're going to end up with making some money. Remember, they have to pay their employees, they have the electricity bills, they have the facility you're gambling in some cases the tables, the machines, and all of those things considered. Now, in the next example, which is example 6, this was just background. What's the odds if you have a pair of fair dice, using 2 of these, to roll a 7? Well, again, if you look at our little chart here that I put up again, how many ways are there to roll a 7 out of the 36 possible ways? Well, there are 6 ways. So 1/36 is 1/6. And what are the other ways that you wouldn't get a 7? Well, there are 30 out of 36 ways, which reduces to 5/6. And you'll notice this comes out exactly to what we had before when we do our multiplication. 1/6 times 6/5, converting this to its reciprocal and division to multiplication, it's 1 to 5 would be the odds. So when you're at a gaming table, your greatest chances of making your point is 1 out of 5 shooting a total of 7. Because notice that no matter what you have on this die, whatever you get on here will determine whether it adds up to a 7. And there are 6 ways. So, I don't know if this is giving you permission when you get old enough to go gambling, but at least you know how the house is, or the rules are supposed to work. Now there is an extra question in the book, part B of this example 6, and there's a matching question. I have written out the matching question. Let's say you bet $5 that an 8 will turn up and you win. What should the house pay you if you put $5 and the 8 turns up? Well, what are the odds that a 5, or what is the probability that a 5 will show up? I'm sorry, an 8 will show up. It's 5 out of 36. 5 out of 36. And then this is divided by, subtract 5 from 36 and get 31 over 36. Change it to multiplication. Here the 36's cancel out, so the odds are 5 to 31. So if you pay 5, the house should pay 31. And that's where that 31 comes from. And again, you're going to do practice and quiz me's, and again, you have to understand the process of what's going on. Okay, moving on to example 7. It starts on page 392. It says, in a repeated roll of 2 fair dice, the odds of rolling a 5 before a 7 is 3 to 2. Now, where did they get that from? Well, if we look at our chart here, to roll a 5 is 4 times. To roll a 7 is 6 times. So there's our 4 to 6, and we can divide each of those by 2, and that's where they get the 2 to 3. Now, in a sense, the 2 is the A, and the 3 is the B. And then they introduced this formula for, it's called, the odds of an event are A divided by, then the probability of E is this formula right here. So the probability of rolling a 5 before the 7 will be, our A is 2, our A is still 2, plus the B, which is 3. Oop. It then becomes 2 out of 5.